episode 15, I am going to talk about what effect the rapid power oscillations may have on fuel failures. How can the power oscillations occur in a nuclear reactor? So there are two ways which I am going to talk about. The first one is on power loading. On power loading for nuclear power reactors means that old used fuel is removed bit by bit and new fuel is loaded without interrupting the power production of the reactor. In this process, the power in the reactor may undergo oscillations. The more rapid the process is, the higher are the power oscillations. The same type of oscillations also take place if the power in the reactor is raised rapidly. The rate of change of power is limited in both the above mentioned processes below a limit. It is observed that if the rate exceeds the allowed rate, fuel failures are observed in high rated reactor channels. That is, if it is exceeded, say in the evening, sometimes the next day, lot of fuel failures in high power channels will be noted. It may occur either due to manufacturing defect, of course, or due to clad temperatures touching the failure point. So I am going to talk about how the clad temperatures may touch the failure point even when the power, that is the steady power, is much less corresponding to the failure clad temperatures. Failure depends on two temperature factors. What is the temperature? The first one is what is the temperature, and second, how long the fuel pins at that temperature stay. But before we talk about it, let me explain what do we mean when we say that fuel has filled. It means that clad boundary has been broken, and so fission gases in the fuel clad gap can come out into the coolant. Normally, it starts with pinholes developing at clad grain boundaries. For most of the zircaloy clad reactor, the failure, that is the development of pinholes, is almost immediate at 800 degrees Celsius. For other temperatures above 300 degrees Celsius, it depends on time, how long the fuel stayed at that temperature. The higher the temperature, the shorter is the time to failure. Today, in this episode, I am trying to reason out, firstly, why do fuel failures occur? And secondly, why do the fuel failures take time of about a day before they fail? As I said earlier, on power rapid fuel loading or along with rapid power changes invariably lead to power oscillations in the reactor core, this is because of a large difference in the thermal time constants and neutronic time constant of a reactor. The more rapid is the change, the higher is the magnitude of oscillations. For a constant flow condition, that is which is true for a pump system, the steady heat flux, that is heat flowing out of the pin versus temperature graph, has a peculiar nature for flow systems. The graph of heat flux versus temperature of the surface is shown here. Those who know this graph know that initially there will be at low temperatures of the wall or at low heat flux, it will be a single phase convective heat transfer which passes on to nucleate boiling heat transfer through a short region of subcooled nucleate boiling. It touches a critical heat flux where the nucleate boiling changes its nature, moves towards the film boiling zone and goes through a transition boiling zone and he touches the film boiling zone. So at a particular heat flux, constant heat flux, the fuel pins will have three operating zones. The first one will be in the nucleate boiling zone, the second in the transition boiling zone, and the third will be in the film boiling zone. The subcooled nucleate boiling zone and film boiling zone, the operating point is in the stable zone, while in the transition boiling, it is in unstable zone. That is, in transition boiling, the point will quickly move away from the operating point, and depending upon how the heat flux is changing, it may go to the film boiling zone or the nucleate boiling zone. So as the power rises, that is, it also leads to heat flux increase, that is heat flowing out of the pin. The heat transfer from the heated surface at constant flow conditions goes through different modes of heat transfer as I told before. That is from single phase to nuclear boiling, then to transition boiling, and then to film boiling. This is classifying it very broadly. For a constant heat flux processes, it has, as I said earlier, it has three operating points. Two of them are in stable region of operation, while one is in unstable region. If you want to know more about it, how and why, a detailed description of this will be available in any textbook on flow heat transfer. Under normal stable operation, the operating point is kept very near critical heat flux conditions, the point where the heat transfer changes from nucleate boiling to transition boiling region. And this is done from economic considerations. That is, the operating point is kept very near the critical heat flux condition. This is the first stable operating point. The second operating point is unstable and is in transition phase at a much higher temperature. The third operating point for the same heat flux is at a much higher temperature in the film boiling region. This is the second stable operating point for a given heat flux. The magnitude of power oscillations in the considered cases will be higher for higher power rods. It is obvious. Consequently, the heat flux, the heat flux which is it's tending to at the fuel pin surface will be higher. We all know that heat flux in the pins is kept high near critical heat flux from economic considerations. If the oscillatory heat flux due to power oscillations tends to cross the critical heat flux, the operating point tends to slide down to the next stable operating point, crossing the unstable point in the transitional boiling zone, where that is the at the second operating point the pin surface temperature is high and the operator would not know this, that it is operating at a higher temperature, because there is no signal indicating this. The operating point now cannot come back to the original point even if the heat flux comes to the normal operating heat flux. That is the peculiar nature of this graph. For doing that, for returning to the natural operating point, the operator has to reduce the power sufficiently below and then increase it. At the new point, at higher temperature, the pin can operate only for a limited time without failure. This time could be a day or more depending on the temperature and the film boiling zone, that is the second operating point. Eventually, at this temperature, the fuel pin fills. The operator observes a delayed fuel failure. Now, some may argue that fuel pin is failing due to thermal shock. But in zircaloy, a very ductile material as clad, this is highly improbable. So let me end this episode here, and next time we'll choose a different topic. Thank you so much.